Hey everyone, we're going to finish up chapter 21 and we've covered all the reactions now. We just want to talk about summarizing them, looking for patterns, and then doing some synthesis and practicing that. So what I recommend is to just get a blank sheet of paper out right now or your notebook and just write down all the lists and let's look for, what are they called? What are the main points to understand about them? And once you have that collection, start writing your mechanisms out. And that way you'll have them all to study from. Okay, so let's start with the first thing we learned was Keto-Enol Tautomerization. You should know the mechanism and the reaction going forward and back and in acidic conditions versus basic conditions. You have water in there the whole time. You just have either H plus as well or OH minus, and they have slightly different mechanisms, so you should be able to do that. So I would write this reaction out. Choose acid or base, write that mechanism, do the same thing, and write for the other one how that works as well. All right, for alpha halogenation, you should be able to start with a ketone or aldehyde, show how base pulls off the alpha hydrogen, and then you can use something like Br2 or iodine or chlorine, and you can halogenate that alpha position. The problem with the base is you get multiple halogenations, so you'll end up with Br all over all the alpha positions. So it's better to do this under acidic conditions if you're looking for monobromination or monohalogenation. So work out both of these mechanisms though and see how that works and why you would get multiple for this and not only mono for that. Okay, it's very different. For carboxylic acids, if you start with the carboxylic acid, you can also brominate, but you have to go through an acid halide intermediate first. And this is the Vollhardt-Szalinski reaction. So it'd be good for you to review what does PBr3 do, what does Br2 do, and then how do you end up with the carboxylic acid again at the end. So it'd be good for you to write this reaction, then leave space for a mechanism and write out that mechanism. For the haloform reaction, we have basic conditions now. So with base, you would get multiple halogenations, and then you would have the hydrolysis occur and have a bromoform at the end. So there's that reaction. And then aldol condensation starts with the addition. So notice we're using 2 of these if it's not specified. And then you have the condensation with heat to remove this as water. Okay, so there's a minus H2O here. With the next one, you have Claisen condensation. So this is the same thing as aldol, except with an ester. So with the ester, then it adds to another one like itself, unless it's specified that there's a different one. The ester adds to itself, and we get this product. So it's a beta keto ester. Whereas here, for the aldol, we had a beta hydroxy ketone or aldehyde. Okay, so there's differences, and I encourage you to look for those differences like here and here. That's going to look different, but if you know the mechanism, you never have to memorize anything. You can just figure it out. That's really what I prefer for myself anyway, and if for you guys as well. Same thing here, like these are basically the same reaction except we have this versus that. So just be aware of that. Will help you figure out which reaction you're supposed to use because they're so similar. You might think, do I just use these reagents or do I need to use PBr3? So the main difference is what you're starting with. Same thing with alpha alkylation using alkyl halide. You just need to make an enolate, but sometimes it matters whether you make the enolate at the more substituted or less substituted carbons. So that's what LDA versus LAH is for. So make sure you know about the kinetic versus the thermodynamic enolate and when to use each one. We also have the malonic ester synthesis, which is where we use a malonic ester like diethyl malonate here. And you can do get a carboxylic acid as your product. Versus if you want to get a methyl ketone as your product, you would use the ethyl acetoacetate instead of the ester here. Okay, but they're all alpha alkylation reactions, and these are alpha alkylation as well. So it's good to recognize that. And then conjugate addition, we talked about if you have an alpha beta unsaturated, this is like an enone or an enal, okay? So this conjugate system, you have this becoming your nucleophile as an enolate to attack at this position here rather than the carbonyl. So those are all Michael additions. If you have something less soft, like just a regular ketone or aldehyde, you can still have it attack here. The enolate, either here or here, can attack here by making this softer through an enamine. So that's where you'll react this first with a secondary amine. All right, and our last reaction we covered was Robinson annulation. That's where we have some kind of a carbonyl group and it attacks 1,4 to this conjugate system and where it was conjugated, and then once you have that added on, you could do an aldol to close it up into another ring. So that's called Robinson annulation, and it's a Michael addition plus an aldol condensation. So once you have an example of each of those reactions, write out the mechanism, and you will get some points for that, but mainly that's important, not for the points, but to actually catalog everything and have it there, tangible for you to use and put into your syntheses. So let's start with some syntheses. Okay, so let's pick up with synthetic strategies right here. We're at the last part of this chapter, putting it all together. So now that you have your list of reactions that you can draw from, we'll start looking for some patterns. Here we're focusing on difunctionalized products. That means two functional groups. So if you notice that you have two carbonyl groups, for example, but you're starting with one, then you know you're going to do an addition reaction of some kind. So for this one, what you want to focus on is the distance between these two carbonyl groups. You can notice the 1, 2, 3, 4, 5 carbons apart. And so what that tells me is comparing this to this molecule, I see that's where it ended up, right? This and this. So I know that this part got added on. Now if I take a look at what this piece is, I have this, but I need it to add on like glue, where this is probably my enolate and this is my positive charge. So how do I get this to be positive? If you remember from some of the previous videos, I want to make it an electrophile by having a pi bond there. So this tells me it's a kind of Michael addition or conjugate addition, but I'm not starting with a Michael donor. This only has one carbonyl. It's not very soft nucleophile. So I'm going to do the Stork-enamine reaction. So that's sort of how I pieced it together, step by step logically, how I know that this is the piece I need, and then this is needed because this only has one carbonyl, not two. And then the water at the end, really you should do maybe some dilute acid or water workup to get this back into its carbonyl keto form. Okay, so again, what am I looking for here? I'm comparing what I start with to my product. I notice that there's this piece missing. I notice that they're 1,5 apart. That tells me that I probably have an alpha beta unsaturated carbonyl, and it's one of my conjugate additions. The next one is to look at, you've got one of these, but now you have a chain. So obviously you have to use two of these to link them together. And this is going to be where one is the nucleophile and it's going to act on another one as an electrophile. How do I know that? Well, I can sort of see it now, but another way you could tell is by focusing on the functional groups that you get. I'm getting a carbonyl and a beta hydroxy group. So beta hydroxy group is from one of these attacking another one, and you get the hydroxyl group from that. So this is my aldol reaction, and it's where you see a beta hydroxy ketone or aldehyde. So beta hydroxy group. Okay, so that's something you want to look for. Another thing you could take away from this is, what if it was the condensation? What if instead of the beta hydroxy group, you got this instead? So definitely you should know, oh, well, this could have been from a beta hydroxy, but then it did the condensation with heat. So then you know that it's the same thing here, but with heat. So just be aware of those things. And then see how these link together? You could feed that into this reaction here, and you could do a conjugate addition after that. So there's some ideas for how to link these together and do multi-step synthesis. Okay, the next one is basically the same thing, but and this 2 got cut off. But notice that instead of a beta hydroxy group, we have a beta keto group. So this is beta keto, or 3 away from another carbonyl, 1, 2, 3. Okay, so we're focusing in on the distance. A 1,5 indicates a conjugate addition, a 1,3 indicates either aldol or Claisen condensation. All right, so this is Claisen. And I know this is Claisen because this is an ester product at the end. Just be aware, though, of the multi-step idea. Is there something I can do with this? Yeah, maybe I can hydrolyze it with some heat. And I would just get, with acid and heat, these will get converted to carboxylic acid, and then this might leave as CO2. So just be aware of the different reactions that can follow so that we could tack them on and build these larger problems. All right? Okay, so let's use that idea, and by indicating where the functional groups end up, we might be able to narrow it down to some of these ideas up here. So for this first one, notice that there's 2 functional groups, and they occur a certain distance from each other, 1, 2, 3, or 1, 2, 3. It doesn't matter. So there's a kind of beta addition, right? So there's a beta hydroxy, or maybe they came from carbonyl groups. So when you want to do this problem, you might think back to, okay, well, maybe I could do some kind of an aldol reaction and then reduce this to an alcohol. So that's what I'm thinking, is it looks most like this reaction, but with some variation. So to know all those variations, well, you can't know all of them, but you probably could just practice as much as you can so that you see and get exposed to a lot of different reactions. For this one, I'm picturing that this came from a carbonyl of some kind. So I'm picturing something like that. And then I picture that this probably got attacked here by another molecule like this. Well, it turns out this is the same molecule, right? So it turns out it is an aldol, where this one became an enolate, and it attacked here, and that became my beta hydroxy group. So if I do that, so notice I'm using mechanism to figure this out. I'm also using a synthon approach where I sort of cut the new bonds. And how did I know to cut here? Was because if you picture a carbonyl here and you picture a carbonyl here, this is your alpha and this is your beta, or this is your beta here. And you can try cutting between alpha and beta. That's usually where new bonds form, because the alpha was the nucleophile attacking carbon. So try to look for that kind of relationship, and maybe you'll be able to break things down into simple pieces. So for this synthesis, we're going to have propanal react with NaOH to do the initial aldol reaction. The product we get is this beta hydroxy aldehyde. So that was the aldol reaction. And notice the carbonyl group here is going to need to be reduced to an alcohol. So we can use NABH4 or LAH to do the reduction of that carbonyl group. And I don't need to protect the other group, but I may need to use an excess, just because the first equivalent might react with the H of the alcohol. So I should write excess NABH4 there. And then you could do that in methanol, or you can do an acid workup step next. So there it is. So for the next one, I just want you to notice the functional groups and go ahead and give those a try and use these up here as a guide for which reactions you might want to look at. And we'll come back and check these together. So for this one, I'm looking at this 1,5 distance between these two functional groups. So that's telling me there's some kind of Michael conjugate addition going on here. The thing is that it's not symmetrical, so there could be two different ways of doing this one. For example, I'm envisioning this being the carbonyl, and this could be my alpha enolate that attacks here. So that means this could be my new bond between 2 and 3, this alpha beta group here. Then that means the other group is this one here. Or I could envision this being the carbonyl and this alpha enolate attacks here, and my perhaps the conjugated system looks like this piece over here. So that's if my cleavage was this way. Okay, so yeah, which one's better? I think either one of these could work. This might be a better enolate than this one simply because of the additional alkyl group. So this might be a little bit better. But either one would work okay. Let's just take this one for example. If I started with this molecule then, right here, I'll have a reaction where I add, let's see, some kind of a base. So first step, and you can use NaOH for this. So NaOH, you make your enolate, and then step 2, you add your unsaturation group here, so your alpha beta unsaturated carbonyl. Then this attacks there. We get the enolate, and then that tautomerizes back to the keto form. What we'll get after this step will look like this. So both of these will be carbonyl groups at the end. So probably what we need to do is reduce them both down using LAH excess or NABH4 excess. Either one's fine. I like NABH4 on carbonyl, like aldehydes and ketones myself, just because I don't think it's necessary to have really harsh LAH around. And then fourth step could be just acid workup to make sure the alcohols are protonated and neutral. So just dilute acid or water is fine. Okay. Yeah, so then now on the next one, these are 1, 2, 3, so 1, 3 away. So this is going to be either Claisen or Aldol reactions. And so I'm going to end up probably before this step was maybe what had happened was that these were carbonyl groups. So I'm sort of picturing that. And maybe before that I had some kind of reaction like that. How do I know that? This is alpha, and so this is beta. So this is a beta keto group. A beta keto group probably came from this Claisen reaction. So I'm going to picture starting with my aldehyde, the one that has an enolate. See, that's my nucleophile is right here at this carbon. So I need that to react with my base in the first step. So my first step is going to be, let's see, NaOH, or it can be any kind of base like ethoxide, methoxide, LDA even. My second part is going to be I need to add this group here. Now this could go two ways. I could either add an ester, and then it'll do sort of this, it'll turn into the enolate attack here and then kick out that group, and that's how we can get a beta keto group. Or I could do another one of these and do an aldol, so I don't really have to say that because it's what I started with. So if I go with the aldol route, I'll just already get this, but it will need to be oxidized because it'll be, an aldol will give me a beta hydroxy group. See, if I do this, then I need to oxidize it. So my second step will be, what do I need to oxidize this? Well, I need to be careful because this is an aldehyde. So if I oxidize this, this could go to a carboxylic acid unless I protect it. But really I just want to make this into a ketone, and PCC will be fine. PCC is not strong enough to oxidize my aldehyde to carboxylic acid. So maybe I'll just do that, and then I'll get my product that way. Otherwise, you could do a Claisen type reaction and have this attack here, and then get my product that way. Okay, so there's multiple options for these, and notice we're using things from previous chapters, NABH4 and PCC, Jones reagent, so just keep practicing on those. All right, for the next problem, we're going to work on using this Gilman reagent. Some of you may or may not be familiar with Gilman. Gilman is an lithium cuprate. What that means is it's got these, it's sort of like a Grignard reaction in a sense. It's got two R groups and this copper lithium part in the center. And the way that this works is this part is partial positive and this part is partial negative. So you get one nucleophile equivalent right here. The other R is not negatively charged. It's just sort of bonded with the rest of this. And that is eventually wasted. But in terms of the R group being nucleophilic, it's very similar to the Grignard reaction in that this is like the part that we don't want and this is the nucleophile that we do want. So when I see this, I basically think of this R group as my nucleophile. So I'm going to put a little partial negative here. But it's only one of the ethyl groups, and it's considered a soft nucleophile, whereas the Grignard reagent or even organolithium by itself, this is considered hard nucleophiles. They're often not going to attack at the conjugate center. They're going to, at the 1,4 addition, they're going to add 1,2. These guys are going to want to attack the carbonyl carbon. This one will be like a Michael donor. It will attack the 1,4 position. Okay. All right, so given that, can we work out the mechanism of what's going on here? So, like I said, this is our nucleophile. So an ethyl group is going to attack 1,4 because it's softer than a Grignard. And then when it does that, we're going to end up with something like this. Okay, and now we're halfway there. We've got our ethyl group on here. So there was sort of a cleavage here. It's ethanol. And now we need a way to add this methyl group. So notice what's going to happen here is I'm going to have this come down, and then this can attack alkyl halide and just do an SN2 type reaction. And that's how I end up with my methyl group in the alpha position. Okay, and that's how I get my carbonyl back as well. So that's the intermediate right here, is this ethyl group added on the beta position, and I have this enolate ion that attacks methyl. Okay, so working backwards then, you're going to have an R group in the beta position, an R group in the alpha position, and you're going to use this organolithium cuprate as your reactant. So let's do one of these together. For this one, notice we're starting with the alpha beta unsaturated. That tells me it's probably going to be some kind of Michael addition. I've got two different R groups here. So first, I want to figure out what do I need to add this group on at this beta position. So that's where I need my Gilman reagent. Okay, so that's that. So remember, there's two R groups, but only one of them attacks. So this one goes here, and then I make my enolate, and it's going to attack at the alpha carbon. I need this group. So to get that group, I'm going to add a halogen on there so that when this comes back down, it'll attack here, okay, when it forms the enolate. All right, and that's it. Okay, so that's my really simple Michael reaction followed by just a SN2 reaction to get alpha alkylation as well. All right, so that's how I can get difunctionality. That means I can get, well, actually these are just R groups, so, but you can get two R groups at least. So that's a nice trick for that. Okay, so in all of these, let's identify what are the two R groups you need, and then some of them have things from before that you might need to remember how to do. So you might need to bring in some reactions from chapter 19 and 20. So get your reaction maps out from those if you need. All right, come back in a few minutes. Okay, so for part B, notice our two alkyl groups are going to be here. There's one right here, and then there's also one right here. And this part is my original aldehyde, but now it's an alcohol. So we may need to tack on an extra step for that part. Okay, so our first one is to add a methyl group. So I'm going to do the methyl Gilman. All right, and then my second one is going to be to add this methyl group over here, but this time it as an electrophile. So this is going to be CH3I, for example. Now don't forget to work out the mechanism so you understand how this works. Okay, how this works is you've got your CH3 of your Gilman. Okay, you have one of them attacking at the beta carbon, and then you have this. And then you get the enolate, and then that enolate comes down and attacks an R group of a alkyl halide. Okay, so that's like an SN2 type reaction. Now after that though, I'm still going to end up with a carbonyl group. This will be an aldehyde still. So to reduce that, I need to use, again, either NABH4 or LAH. And then I like to just add an acid workup step, although your book has this done in methanol. Okay, for the next one, I'm looking at a couple of things here. So first, I have an R group added on here at the beta position, alpha, beta here. Then I have an alpha position one here, and then I have this aldehyde that has converted to an alkyl halide, acyl halide. So, oh wow, that's a lot of stuff, right? So first, I think you know the first two steps. You need this Gilman reagent here, and you need this methyl halide there. Okay, so we're going to definitely do that. And then for our final steps 3 and 4, we're going to oxidize this to a carboxylic acid. So steps 1 and 2 will be the same as above. And our third and fourth steps will be to oxidize this to a carboxylic acid, so OH group here, and then use thionyl chloride to get the chlorine on there. All right, for this one, hopefully you saw that you have to convert this to a carbonyl first, so that I could do a 1,4 addition of a carbonyl group. Otherwise, this does not react here, right, or here, because there's no conjugate system. So to do that, we will use acid to hydrolyze it back to the carbonyl group. Okay, so basically that mechanism was to make one of these into a leaving group, and then this one comes in and that one opens up, and then eventually you'll be able to get the carbonyl back. Okay, and with water attacking as well, you have to hydrolyze this off. Okay, that first step is going to give you a carbonyl group here, and from there we can do our 2 alkylations just like in the other problems. Okay, and here we need to do this in steps. So our first step will be reagent there, and then 2 we'll use an ethyl halide like ethyl bromide or something, or ethyl iodide. And then the third one, well, at this stage, what do we get? We'll get this with our ethyl group and our ethyl group like that. And then all we need to do to get it back to here is to make that back into the acetal. So that's where we need, and hopefully you guys remember, you need ethylene glycol and some catalytic acid. And our last one is, or we have 2 more. This one is a conjugate addition after we oxidize this. So our first step will be to oxidize this to my aldehyde, so PCC. I don't want to make a carboxylic acid because that H on the carboxylic acid will be acidic, so I don't want my Michael reaction to go wrong with that. Once I have PCC, this will become an aldehyde like this, okay? And then I need this group added onto it, right? Or no, let's see, I need this group added onto it. So how do I know that? Is I'm sort of outlining this part is really this part. So this imine is going to be my C double bond O. I have an alpha, beta, gamma. So that's my carbon skeleton here. So this is my first addition, this is my second addition, and then I got to convert it to an imine. And this last one, finally, same idea here. I'm going to use PCC, and then here's my conjugate addition. I need to add a methyl group here, and I need to add a methyl group here. All right, so after this part, we get this aldehyde back, but we're trying to reduce that down to a methyl group, so we want to get rid of the C double bond O completely. So we want to replace it. So what we do is we could either do one of these two reductions from earlier in chapter 19 with the aldehydes and ketones. You could either do Clemmensen reduction under acidic conditions, or you could do this Wolff-Kishner reduction under base, and that just gets rid of the double bond O. All right, so now we're just going to do a bunch of practice problems just so you get used to this chapter. And here's a little outline of some of the ideas. This is from an earlier edition where this was actually chapter 22, but for you guys it's 21. But do read it and see if it helps you. And then I recommend these problems from the book just for practice, and I have the answers right here. So that's pretty much the end of chapter 21. I'm going to stick around and I'm going to help you through these if you want, but you can just do them for homework this time. So just work them out on your own when you have a chance.